Okay, we come to another temporal characteristic of the response of a linear time invariant system. So we know what is a how to calculate the response of a system. Y of t is simply given by the convolution integral, or it is the convolution operation between, sometimes called as convolution multiplication between the input x of t star h of t, where h of t is called as the unit impulse response of the system, and the unit impulse response h of t is the characteristic of the system. That means it completely describes LTI systems. So each LTI system will have a different function of h of t. Okay, like just like you have a different name for each one of you, right? So the unit impulse response h of t will have a different function for different type of systems. Okay, let's keep it that way. Now we know what is the autocorrelation function. Can you recollect what is the autocorrelation function? Okay, autocorrelation function of a process. Normally, how is it denoted? It is denoted as capital R subscript capital X of T1 comma T2. Now, if the system is a Whiteson stationary process, then the autocorrelation function is simply given by, is only a function of the time difference between these time points, right? Rx of tau. So it is a function of only tau, Rx of tau. Now here, what is meant by the autocorrelation of response? So in fact, we are interested to find out, determine when the input to the system is a random process, capital X of t, what is the autocorrelation function of its output? We know we have already come across this. Y of t is another random signal that comes from the ensemble of random signals of the process y of t, capital Y of t, right? Y of t is simply a library of these various types of these random signals, and simply the output can be any one of these with associated with some probability of occurrence, right? So input is a random process, output is a random process, and we have a linear time invariant system in between, and we are interested to find out what will be the response of the system to the when the input is a random process, and the response of the system is also a random process. We have studied so far, and we have calculated what is the mean of such a random process and what is the mean square value of that random process. Both are two types of temporal characteristics of the response. Now we come to the third type of temporal characteristic called as the autocorrelation function. Here anybody doesn't know what is the temporal characteristic? Temporal characteristic means the time characteristic. Temporal means time characteristics. Here all these functions are with respect to time, as opposed to being a spectral characteristic. In the spectral characteristics, all the functions will be functions of frequency omega. Okay, so this is autocorrelation function which is defined on the time axis, and it is a temporal characteristic. Now we are interested to find out the autocorrelation of the y of t. Now so I want to find out the autocorrelation function. I want to determine this left hand side, or y of t is the random process at the time points t and t plus tau. We are interested to find out the autocorrelation at these time points. Now of two variables at these time points. Now that will be given by the expectation of the product of these two random variables at those time points. That means expectation of y of t times y of t plus tau. Now expanding this expression, I can use the response of a LTI system. That means this is the y of t, which is the response. Now the response of a LTI system is calculated by using the convolution integral. Simply that is the convolution between the input and the impulse response of the system. Okay, so h of t, when h of t is the impulse response of the system, it will be given by this expression, that is my integral minus infinity plus infinity of h of tau and x of t minus tau d tau. Simply for second y of t, it is customary to use a different random dummy variable, and normally we have used tau 2. Now simplifying that expression, what will happen? Now let us see, observe what are the random variables and what are the deterministic variables or functions in this expression. Now expectation of integral is given by integral of expectation. That means we can always take this expectation inside this integrals and we can apply to the expression on the inside, right? So what are the random variables in this expression? Here the x concerns x of t. X of t concerns is one random variable, and similarly x is also another random variable on this side. So we can join this together and apply expectation to the whole term. What will happen if I apply the expectation to this term? And normally the constants are h. The h's, they come outside this integration. They normally come outside this expectation. We can write this expression as the following. Anybody has a doubt? Now let us assume that we have a Whiteson stationary random process as input. Then how is the expression of this output? The expression of the autocorrelation of the response changes. Now that is even equal to, now what? Now, so I have applied, this is a double integral minus infinity plus infinity of what? The expectation of x of t minus tau 1 times x of t plus tau minus tau 2, multiplied with both of these. H is a deterministic function and h of tau 2 is also a deterministic function. Now how would I write this expression? What is inside this integral, in this expectation? How can I write this expectation as? Now you recollect this one again. You have to call this as the expectation of the product of the random variables at the time points, which is t minus tau 1 and another time point t plus tau minus tau 2. Okay, so when we have expectation of a product of these two random variables at different time points, this is called as the autocorrelation of the random process x. Therefore I substitute that there, that is Rx. Now simply because x is a set is called is given as a Whiteson stationary random process, we can take that autocorrelation function is only a difference of these time points. Now how do I take these time points? Difference of these time points, is it this minus this or this minus this? Normally it is, if this is called as t1, this is t2, then we have to calculate the difference as t2 minus t1. Therefore this time point minus that first time point. So the second time point comes first, this comes next. So the difference of this and that, would be t plus tau minus tau 2 minus t plus tau 1. That will give you this time point, which is the difference of these two time points. Now, another thing. So this is the autocorrelation of the input. So we can calculate the output autocorrelation as the double integral of using the autocorrelation of the input and the unit impulse responses of the system. Okay, this gives you a closed form expression of the Ry of t. Now one more thing, in the above expression we have actually taken the left hand side to be Ry of t comma t plus tau. So far we don't know whether this is the expression which is independent of time, right? We don't know because input is given as a Whiteson stationary process, but we do not know whether capital Y is also Whiteson stationary. To see that, now look at the right hand side of whatever the final expression we have got. Now this is the expression. Do you see the time point t, the variable t, anywhere in this expression? So this is expression. Again, tau 1 and tau 2 are dummy variables. That means this is a definite integral. So the dummy variable goes away in the integration. The tau 1 and tau 2, they integrate out. And whatever left is only a function of tau. Okay, it is very important to see that this entire integral is only a function of tau. It doesn't dependent on small t. That is why the left hand side of this expression is kind of modified and written as Ry of tau as the time difference between the time points. Now when you have this type of autocorrelation function, that is a function which is a function of only the time difference between these time points, then we have satisfied the second condition of the Whiteson stationary process. Okay, now what about the mean of the process y of t? We have calculated in this that mean in the previous lecture. The mean, when the input is a Whiteson stationary, the mean is also a constant. The mean of the response of the system is a constant. That is, the mean of the output random process is a constant. Therefore, we also satisfy the first condition of Whiteson stationarity. Hence, in fact, we can call that this random process y, capital Y, is also Whiteson stationary process. It is very important to see that. Okay, so the outcome is that when your input is a Whiteson stationary process, that is capital X of t is Whiteson stationary, then the output of a linear time invariant system, okay, it cannot be any type of system. The system should be a linear time invariant system. Then the response of that type of a system will also be a Whiteson stationary process. That means X of t is Whiteson stationary, the input and output Y of t will also be Whiteson stationary process. That is what we have to recognize. Okay. So you please practice these expressions. These are very simple, and if you have further questions, you can ask me uh, during the regular hours whenever we have a meeting during our university time. Now, any questions about this? So autocorrelation of function of a response. Thank you very much.